All right, welcome back again. This time we want to look at one-way ANOVA in past, one-way ANOVA in past. And you can understand so far we have been dealing with data set that has one numerical variables and two groups basically. So far, that is both pair and unpair t-test. One-way ANOVA is also a t-test actually, but in another form, which means in when your categorical data or factor data is more than two groups, then you use what is called ANOVA. All right, analysis of variance. That's what it means. So I don't need to go to definitions or because it basically means to compare the means of more than two groups. Okay, of more than two groups or samples. That is what one-way ANOVA is talking about. Okay. The data set here you are seeing have been used already in R. If you have listened to my R's channels, you can see that my R videos, you have seen that the data I've used the data before. Okay, this is a categorical variable here called sites. There are 4 sites here. Okay, 4 sites here, and each of elements here. Okay, 4 elements here. So we just start to give us this is called poetry data. This data is called poetry, which can be gotten from a car data library in R. All right, just when you install a car data library now, you can run this particular data called poetry data. All right, so it has 4 groups, as I said. So from this data, you can develop an hypothesis. For example, can maybe probably want to test whether the mean of aluminium or iron or magnesium or calcium or sodium, want to test whether the mean of any one of them, the mean of aluminum, for example, composition is differ in the 4 sites. Okay, whether the mean differ in 4 sites. So you can plot a chart to see that first, which we have done in R before, which clearly shows that by looking at the mean or median or maybe using something like a bar chart, you could have seen that the mean differs actually, but you want to test. We don't want to conclude by mere graphical presentation. We want to conclude by statistical test whether the mean actually differ, whether it's not by chance. Okay, so we now run what is called ANOVA test. So this is a one-way ANOVA. We have also 2 ways. In fact, we have 3 ways ANOVA. If you check my video on R for statistical testing, you see 1 way, 2 way, 3 ways. Okay, and more ANOVA test there. So, but I want to look at the one-way ANOVA here and see from each one. Now but you have to use this and one of these. Okay, to test. So we need one numerical variables, which is any one of these ones. Okay, and we also have one categorical variables, which is this. So because this one is 4 groups now, it means more than 2. So we need more than 2 groups. So this is 4 groups now. All right. So now we can go ahead and do the testing and check if. So let us first copy this to pass first. I just need from here. Let's copy from here to pass. So as usual, space here. Now when you post, you have to make this particular one your group field. You just select group here for site. Right, it's very important. Else you cannot do much. So that it has been. Can you see showing G now? Okay, so then we want to use any one of these. Okay, but which one of them is a meet parameter assumption first? That's what we want to use from these 5 numerical tests. Okay, numerical values or numerical factors. I mean, sorry, this numerical numbers, variables. So which one of them meet assumption? So let's see first. Want to check for Shapiro. We can do together all of them. So, but let's do here normal test. You can see that this one meets assumption 0.09 is higher than 0.05, so it meets assumption. So let's try for iron also. Oh, iron does not meet. Iron is already significant, so it does not meet parametric assumption. So and let's see magnesium. That one also does not meet. That one's already higher than 0.05. I mean, it's lower than 0.05. But of calcium, is already that calcium is okay. Calcium is okay. Calcium can be used because it's just 0.054 or 55, which is not significant. It's not less than 0.05, so it can be used. But of sodium, cannot. So this sodium is 0.000, already past normal, so it cannot be used for. It does not meet absorption for parameters. So can say only aluminium and calcium meet absorption. So we use any one of the two, but we can use this one because this one meet more. So let's choose this. We click on this side, this one, and this together. So if you want to use for aluminium, just click on this and hold down your shift key and click on this. I mean, control key. You go down your control key and click on this. All right, so that's what you do. But we are using this and this together, so just select this together. All right, so this is what. So you now go to your univariate as usual. Okay, this time around now you go to ANOVA. All right, click on ANOVA test here. So we click on this ANOVA. Now it gives you one way ANOVA here. You can see here. Here you can see your result here. You have a between groups. Actually, your between group is actually your values you are looking for. The sum of square is 175.61. Degree of freedom is 3. Mean square is 558.53 or 54. F is equal to your 26.67, and your p-value is equal to 0.00 or 1.62 raised power 0.07. I mean, power 07. So this is just what you are looking for. This the total here is your residual when you have calculated the within groups. Okay, so we don't need this for now. We only need this between groups. That is our site. That's our site. Our groups. All right. So that's what we need. So if you want to do further, okay, let's just let me show you the result in R to compare with the result we got in this past. If you compute this in R, all right, in R, look at this here. You compute this in R. If I follow my R tutorial, you see that this is what we got in R. Look at it. Degree of freedom is 3. Okay, sum of square is 175.61. Okay, mean square is 58.54. And which what we have F is 26. You can see the result here. What you got here and what you got there. Can you see? Let me see if I can bring them together. I'm going to see if I can just let's now cover this surface. All right. Okay, good. So now let's compare directly from here. Now look at it. Between groups, this is our site. We have some square 75.61. Same thing here. Our mean square 58.54, 58.53 is happening to 54 actually. Our F 26.67, same thing here. And our p-value, look at p-value 1.663 is per exponential 0.7, the same thing here. Can you see? Nothing different. So everything is perfect, the same. In fact, your residual is showing the same thing, 22 degree of freedom and 48, you can see here. So you just have your data complete set, all right? Which is a within group, residual is within group. So just have everything perfectly set here, all right? So you have no problem. Within group is residual here, all right? So it is complete. But you may want to do further. Maybe you want to find the effect. I mean the pairwise, okay? The pairwise using maybe Turkey's pairwise, okay? To find which group contribute to this data among those 4 sites. This site, that is it just one site? Is it by chance? Is it one just want to further know that okay, now we have known that okay, this is significant. Which site make it significant? We have done that in R before, so we can use a pairwise here. Okay, just click on pairwise, right? And see the pairwise here. So these are the p-values up here. So you know how to calculate this p-value. These are the corresponding Turkey's Q below. So here you can see them here, the diagonal here. Okay, so if you check the same thing in R here, can see in R, which I computed pairwise here also. Turkey's multiple comparison of means. You can see under 95% confidence interval. Look at the same thing we did here. Right, so look at the result here. We have Caldicott pairwise. These two pairwise Caldicott and actually race. This two will give you 0.0087, significant. With adjusted p-value here. All right, you can see this lower. This is the difference. This lower boundary, this upper boundary. Okay, so you can see here. There are 4. 1, 2, 3, 4. 4 that are significant here. Even after the adjusted p-value, this value is actually Bonferroni. Okay, this Bonferroni adjustment. Okay, so only 4. Let's see here. See here, we also have only 4 here. Look at it. The first one here is significant. This one, and this one. See, and when you look at it in the diagonal, the intersect here, you can see that this one is we have Linden and Ashton here. You can see here, give you 1.5. Okay, same thing here. Linden, Ashton. Where is it now? Okay, look at it here. This last one here. Okay, this one. So 0.0000. Okay, you can count it 1, 2, 3, 4, 5. Can you see? So same thing here, right? 1.5. This one 1.6. 1.6 now. This can apply to 1.5. So you want is 0.008. Okay, count it same thing here. This is for Ashley Ray and Caldicott. Caldicott. Okay, Caldicott and Ashley Ray. Look at it. 0.000887, and we have here 0.00087. Can you see? So everything is perfect, same, no difference. So and this one is so easy to compute. Can you see? Just click on one way here. Click on the tab here. Turkey pairwise. You get your everything you need. So you don't need to do complicated coding to get the result. Just by clicking, you get your result. So that is just one way ANOVA, and together with a pairwise, Turkey's pairwise result. So I think this is very simple to follow, and I think we can meet again in the next class. Thank you for now, and I'll see you next time.